Hi, this is Kevin, and I'm going to lead you through the continuity tutorial, Passive Inflation of a Left Ventricular Infarct Model. The tutorial will consist of 4 parts: loading the mesh, setting up the biomechanics problem, solving the biomechanics problem, and analyzing the results. Step 1. Loading the mesh. We will not focus on mesh generation in this tutorial. Instead, we will start with a pre-built mesh that has been deposited in Continuity's public repository. Let's go ahead and load the model to take a look at what we will be working with. To load a model from the database, select File, Library, Search. We'll search for this model by its ID number, 1161. To load the model, right-click and select Load. To start fresh with this model, we'll select to reset continuity. Now that we've loaded the mesh, let's explore the model. All of the components of the mesh are found in the Mesh Edit menu. We'll start with the first option, the coordinate system. You can see that we'll be working in a rectangular Cartesian coordinate system. Next, let's look at the material coordinate model. Mesh, Edit, Material Coordinates. The material coordinate model allows us to define an orthonormal transformation that rotates the global Cartesian coordinates at any point in the mesh to the local orthonormal material coordinates. Here we are using the standard material coordinate model for continuity titled MatCoord Standard. The material coordinate model editor is one of a number of forms in continuity that allow for user-defined functionality. The input for all of the model editors is written in Sympod, a symbolic Python language. This is then translated into more efficient C code. The C code must be compiled before it is run. Therefore, we will compile the material coordinate model now. You can look at the Python shell in continuity as the model is compiling to see what is going on and if it is working right. And there you see we got the pop-up screen saying that the model compiled correctly, so we're good to go. But before we leave the screen, let's look at the parameters that are in the material coordinate model. This is how we apply fiber sheet and normal angles in continuity. If we click on this, and we will see that currently no fiber angles are defined. We're going to change that to using the fiber angles that are in the field fiber angle. So with that, we'll select OK, and that change has been made and the model has been compiled. Next, let's look at the basis function form. I should have basis, and we'll see that tricubic and trilinear basis functions have been loaded, as well as a few different 2D basis functions. Looking in the nodes form, we can see that this mesh has 80 nodes, and the geometric coordinates are modeled using tricubic Hermite basis functions. If we click onto the fiber angles tab, you'll see that the fiber angles field has fiber angle values in it defined in radians, and this was the field that we set the fiber angles to in the material coordinate form. Lastly, you'll see that in field variable 1, we have a linearly interpolated field, and what is in this field is the scar data. And we'll get to that later when we talk about the constitutive equation. Lastly, let's look in the elements form, and we'll see that this mesh has 32 elements. So we have 80 nodes and 32 elements. Let's go ahead and send the data to the server, calculate the mesh, and we'll render the lines. So now we can see our left ventricular mesh. Move it around so we get a better view. We can also render the inner surface of the LV, and we can look at what our fiber angles look like. And we can render our fiber angles to see what they look like. And if we zoom in on the fiber angles, you can see that they have that characteristic distribution for the left ventricle with about negative 70 degrees on the epicardium, circumferential in the mid-myocardium, and plus 70 to plus 80 on the endocardium. So that's what's in the mesh module for continuity. Now we'll move on to step 2, setting up the biomechanics problem. Similar to the mesh module, the inputs to Continuity's biomechanics module are found in the biomechanics edit menu. Here you will see 4 options. Since we will be performing a passive inflation, we do not need to worry about the dynamic model editor, and we can start with the constitutive model. This constitutive equation is a transversely isotropic model where the stresses are an exponential function of the strains. You can see that there are 5 parameters that describe the behavior of this model: fiber strain coefficient, transverse strain coefficient, fiber trans shear coefficient, stress scaling coefficient, and the bulk modulus. If you look at the stress scaling coefficient, you will see that its value depends on the value in field 1 of the nodes form, which was a measurement of the scar. This constitutive equation changes the material parameters based on the presence or absence of the scar tissue. Once again, we're going to compile this model. And you can see in the Python shell that the compiler is working, and it was a successful compilation, which is good, so we'll select OK. Before we move on to the boundary conditions, we're going to do biomechanics, update, initial conditions with undeformed nodes. And now we'll go ahead and open the boundary conditions form. Biomechanics, edit, boundary conditions. In this first tab, you'll see the initial conditions for each of the nodes, each of the 80 nodes that we have in here. Deformed coordinate 1, deformed coordinate 2, and deformed coordinate 3 put constraints on our model to keep it from moving in non-physiological ways. And the external pressure tabs defines how we're going to apply a pressure to this model. And you'll see that the circulatory model pressure type is selected, and that it's going to be applied on the LV endocardium. So we'll have to look into the circulatory model editor to see what pressure it is that we are applying. So we'll go ahead and press OK. Biomechanics, edit, circulatory model editor, and OK. And you can see our initial condition is we start with a 0 pressure, and we are going to apply a 0.02 kilopascal pressure increment per time step. And with that, we're ready to go ahead and start solving our model. To solve the biomechanics problem, we'll select Biomechanics, Solve Nonlinear. And here we'll take time steps of size 1.0, and we'll take 10 of them. This will apply that 0.02 kilopascal boundary condition 10 times, so that our final pressure will be 0.2 kilopascals. We'll click Solve, and you can look in the Python shell and watch the progress as Continuity solves the problem. So you may want to pause it here, because I'm going to skip ahead until Continuity has finished solving this biomechanics problem. Once it is solved, and you can see that it's solved all the way up to a pressure of 0.2. You can see that in the Python shell. Once it is solved, we are ready to go ahead and analyze the results. So to do that, first of all, we're going to hide some of the things that we currently have rendered. Next, we're going to render the deformed mesh. And we'll change the color of that. To red, and you can see that the mesh has expanded with the internal pressure, which makes sense. Next, let's go ahead and render the fiber strain on the inner surface. Before we do that, we'll have to, when you render stresses or strains in continuity, it saves those as a field variable in your nodes form, and since our field variable 1 already has the scar data in it, we're going to initialize field variable 2. So we can go biomechanics, render surface, and let's render We're going to switch this to field variable 2. We'll render it on the deformed mesh. And let's render the strain. We'll render the Lagrangian green strain in the fiber direction, the 0, 0 direction. And here's that fiber strain. You can get the color bar by looking in the open mesh controls. And we didn't inflate it a whole lot, but you can see the blue is less strain and the red is more strain. And one thing that you'll notice is there is a region, near the apex where there is less strain compared to the other areas around it, and that is actually the area that has the infarct in it.